Okay, we're back. There is this worksheet called Practice with Integration, and I think it's mostly pretty straightforward, but maybe there are some tricky bits. This number 1 says, what is the limit as n goes to infinity of the sum from I equals 1 to n of, and then there are these sort of big parentheses, 3 over ni minus 2 squared plus 1, oh boy, smaller parentheses, is that, do I have that right? Oh no, actually, sorry, times 3 over n, and it's understood that like this is all being summed. Okay, what is going on here? Sort of out of the blue, we are being presented with a limit. Okay, a limit as n goes to infinity. And either this limit doesn't exist for some crazy reason, like it goes off to infinity or oscillation or something like that, but okay, that's not going to happen. If this limit exists, then the answer is going to be a number. Okay, what number is it? Well, we're summing up a whole bunch of things from 1 to n, and okay, this is all just very complicated. In fact, you should, if you're experienced, and we've been doing this all week, you should recognize this as a Riemann sum. Okay, so some Riemann sum is being presented to us, and we're being asked to find the limit as n approaches infinity of that Riemann sum. Well, that's just the definition of an integral. In other words, the way to do this problem is to interpret this limit of a Riemann sum as some integral, and what integral is it? Well, that's what I need you to figure out, right? So there's some, I'll write it in blue because I don't know any of these things. There's some function, but I don't know what that function is. And there's some lower limit of integration and some upper limit of integration. And for all of these things, I don't know what the function is. So question mark, question mark. Okay, in other words, what we are doing is essentially we are practicing how well you know and understand the definition of an integral as the limit of a Riemann sum by presenting you with the limit of a Riemann sum and asking you to reconstruct what integral this represents. This is the analogous question to the kind of hard questions, some students find them hard, that happened 6 weeks ago or something when I gave you a, say, for example, the limit as x approaches 5 of like, you know, okay, this one's really obvious, root x minus root 5 over x minus 5, and well, this is just a limit. And you could, actually, this is somehow too easy. Let's make these cube roots or something. Okay, and this is the limit, and assuming this limit exists, the answer is going to be a number. And you could, if you were very, very crafty, but knew nothing about derivatives, you could attempt to sort of do this limit using some advanced algebra and figure some things out. But actually, what you were supposed to do is interpret this limit as a derivative. And if you recognize that this is just the cube root x function at 5, then this is just for a x which is a tiny bit bigger than 5. This is the change in the cube root function over the change in x. And so therefore, this is supposed to be the derivative of the cube root function at x equals 5. Okay, that's getting a little sloppy. And then you are expected to just do this. And the derivative of the cube root function is 1 over, or rather it's, oh man, what is it? It's 1/3 x to the negative 2/3, so it's 1 over 3x to the 2/3, and so the answer to this limit is 1 over 3 times the cube root of 25. Okay, that's sort of irrelevant, but it's relevant because it's the analogous kind of question. Once you define a derivative as a limit, then you can be asked to do a limit, but the way to do that limit is to figure out what derivative it is and then do that derivative. Okay, so this whole thing we're doing right now in this number 1 and number 2 on this worksheet, maybe it's the hardest part of the whole worksheet, is understanding what's going on here enough so that I can answer these questions. Okay, and there are all kinds of, and they recently, I think starting maybe 1 year ago or 2 years ago, put this topic on the AP exam, and it's just completely freaking out math calculus teachers all over the country and students because they don't know how to do this problem. It's considered very sort of hard. It's because they want you to really understand what an integral is, according to the definition. So there are all sorts of cheap sort of tricks to do this, but I think the best thing to do is to just understand what integration is. So we're going to make a picture, and there's some flexibility here in how you do this. But personally, to me, I see several things going on. I see that there are ultimately two things being multiplied. This thing and this thing. And that's what a Riemann sum is. It's a sum of a bunch of products. Those products being the width of some interval and the function evaluated at some sample point on that interval. And once you just see that, okay, now we're just kind of done with the problem, right? Because if delta x is 3 over n, and the number of rectangles is certainly n, then if delta x is 3 over n, but the width of each subinterval is also just b minus a over n, this tells me that b minus a is 3. And so we must be integrating over an interval of length 3. And here, what are we plugging into that integral? Well, what function do we seem to be integrating? Well, there's actually more than one answer here, but one answer, I think the simplest answer, is that this function is just the x squared plus 1 function. In other words, if you just look at this and see, if you think of this 3 over ni minus 2 as being the input to this function, then it seems that the function is just the function x squared plus 1. This is not the only answer, but this is an answer. Okay, if that's the case, then what would it have to be like for me to be plugging in 3i over n minus 2 sort of over and over again? Well, let's just let I equal 1. When I, because that's the first thing I is after all, so when I is 1, this is negative 2 plus 3 over n. In other words, go way back here to negative 2, and the very, very first number that I'm going to be plugging into this function is negative 2 plus 3 over n. Okay, what's the next number I'm plugging into this function when I is 2? Well, now I'm plugging in negative 2 plus 2 times 3 over n. That's negative 2 plus 2 times 3 over n. And when I'm plugging in I equals 3, I'm getting negative 2 plus 3 times 3 over n. And so now we should start to recognize this. It's very familiar. This is what we have been doing for the past week. It seems as if we are following our RAM. And okay, I'll now draw the x squared plus 1 function. At negative 2, it's going to be up here at 5. And by the time I get to, well, and then something like this. So if that were my function, x squared plus 1, then it seems like if I was going to do this problem, then I would start by drawing rectangles. I am implicitly using RRAM here, and these are exactly the x values which I would plug into my function to do RRAM. And I keep doing this until I plug in my last sample point, and my last sample point is when I is n, and when I is n, then I'm getting 3 minus 2, which is 1. So I'm right here at 1, otherwise known as negative 2 plus 3 over n times n. And so my nth rectangle, oh man, it's taking way too long, is this one, and therefore I conclude that the integral that this Riemann sum represents is the integral from negative 2 to 1 of the function x squared plus 1 dx. Okay. I think that is the simplest way to do it. Just plug in I equals 1, plug in 1 for I, plug in 2 for I, plug in 3 for I, think about what's going on, make a picture, understand the process, and then this is a kind of confirmation, right, that this interval has width 3 from -2 to 1, so it seems like we're doing it all right. Okay, and I'm not going to bother doing that integral right now, but if you watch the previous video, I think you can tell me what this is. Almost in your head, maybe, because we agreed that from -2 to 0, that's going to be 8/3, and from 0 to 1, that's going to be another third, so that's going to be 3, and then this is going to be another 3 times 1, so I bet this is just going to be 6. I hope I have done that right. If not, that's embarrassing, but I think that's just right. Okay, and if you didn't know what I just did there, who cares, because you weren't actually tasked with finding the value of the integral, you were just tasked with writing the integral. So the answer to this problem is that. Okay, let's do one more of these. Try to go a little bit faster. We're taking the limit as n goes to infinity of the sum from I equals 1 to n of the cosine of pi over ni plus pi times pi over n. Alright, well, something very similar is happening here, and then all this is being summed. So once again, this is some integral, and I don't know what that integral is, so I am ignorant both of what function is being integrated and where to start and where to end, and that's the whole point of this problem, is to figure out what these three things are. Okay, but here I think this one is sort of somehow even easier, because if once again I have a sort of a value of a function times a width, and so I interpret this as my delta x, and this as my f of x sub I star, and that's just a Riemann sum. Well, if delta x is b minus a over n, and it's just this pi over n in this case, then I conclude that that b minus a is just pi. So the width of this interval that I'm integrating over must be pi, and okay, once again, I think this is not the only way to do this, but I'm going to think of this inside as being like my input. So if this is my x sub I star, that green circle I just made, then my function is just cosine. So I'm just sort of concluding over here that my function is the cosine function. Again, once again, this is not the only answer, but this is a way to do this. And if this is the cosine function, then I can graph the cosine function. I know exactly what it looks like. It's going to look like this, give or take. Sorry, sketching this on some weird angle. Okay, and what kinds of things am I plugging into the cosine function? Well, the first thing I'm plugging in when I is 1 is pi plus pi over n. In other words, the very first input right here is pi plus pi over n. And what's the next input? Well, when I is 2, I'm plugging in pi plus 2 times pi over n. And when I is 3, I'm plugging in pi plus 3 times pi over n. Continuing until I get to I equals n, in which point I am plugging in pi plus n times pi over n, otherwise known as 2 pi. And so it seems that my rectangles are going to basically be like this. My first rectangle is drawn at a point which is a tiny bit bigger than pi, and etc., and this understanding seems to suggest that I am integrating the cosine function on the interval from pi to 2 pi. So that's exactly what this is. It's the integral from pi to 2 pi of the cosine function. And that's all you had to do for this problem. but also just by looking at the geometry of this picture, it strongly suggests that the answer here is 0, and that's in fact right. Okay, good. That was like a theoretical kind of opener. We're actually going to do more with this later, so I will leave that alone. And yeah. Okay, next comes just a whole bunch of simple, easy problems. Let's see, I have 8 of these, so I'm just going to do them somehow. Maybe, did I think this through? Not really. But okay, so 3, this is number 3, this is number 4, 5, matching the structure of the paper, this is 6, 7, 8, and alright, so this is kind of like what happened in the video. This is a basically geometry exercise. So I'm going to actually just write all these right now. This is pretty terrible. Root 2 to root 18, root 2 dr, and -2 to 4, x over 2, that's 3. This is called integration by geometry. This is what people call this, root 9 minus, or what I call it, integral from -2 to 1 of absolute value x. And then it does get a little harder, integral from -1 to 1 of 2 minus absolute value x. Okay, but I think I did something like this in the other video. And then finally, integral from -1 to 1 of 1 plus root 1 minus x squared. And here we have the integral from a to 2a of x dx. Okay, so for each of these, here's what you're supposed to do. Draw a picture and then just do it, man. So let's go. Integral from -2 to 1 of 4. Okay, this is pretty silly. Here's -2, here's 1, here's 4, and so this shape is just going to be a rectangle. And that rectangle has area 12, so the answer to this problem is 12. Okay, what now? Now we are going to, once again, this is a constant function, height root 2, and we are going from root 2 to root 18, which is just 3 root 2. And so this is once again just a rectangle, and the dimensions of this rectangle are 2 root 2 by root 2, and when you multiply those together you just get 4. So this is just 4. Good. Next, the integral from -2 to 4 of x over 2 plus 3. Okay, so this is just a line. So this shouldn't be too hard. Switching back to black for some reason. When I plug in what is this? Have I made a bad picture here? Maybe. So 1, 2, 3 is the y-intercept. When I plug in -2, I get 2. Yeah. And 2. When I plug in -2, I get, oh my god, I get 2. And when I plug in 4, I get 5. So 1, 2, 3, 4. So okay, algebra 1 challenges there, but I have mastered them. Okay, and so this whole problem just reduces to, can you find the area of this trapezoid? And I can. The area of this trapezoid is going to be the average of the bases times the height, and this is 2, and this is 5, and the height of the trapezoid, which is this dimension, is 6. And so the area here is going to be the average of the bases times the height, so that's 21 is the answer to that. Okay, 6, integral from -3 to 3 of root 9 minus x squared. Well, what's that? It's just the semicircle radius 3. Well, okay, you're supposed to just know that. I guess you all do. Also, we covered this in the video. So semicircle, radius 3, centered at the origin, top half of it. And so this problem just reduces to what's the, well, if you have a circle of radius 3, pi r squared says that the area of that circle will be 9 pi. So this is just going to be 9 pi over 2. Color scheme totally off here. Integral from negative to 1 of root x. We did one exactly like this in the initial lesson. It's going to go like this. And so you're expected to just be able to compute with a combination of graphing skills and geometry that's 2 triangles. The triangle on the left has area 2, and this triangle has area half. And so the answer to this problem is just 5 halves. Good. What else? Here's one that's a little bit harder. 2 minus absolute value x. There's a problem exactly like this on the homework from the book, which we already went over. What does that look like? Absolute value upside down moved up 2. So this function, boom, boom, is going to be 2, and then it's going to be like boom, 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 and it's going to look like this. So this is what the 2 minus absolute value x function looks like. But I'm only interested in the area, the integral from negative 1 to 1. So we do this, and I have to find the area of this little house, and it's just 3. Okay. More. This next one. Okay, you can do this by splitting it up into 2, or perhaps it's more fun to just draw the picture. So if you draw the picture, what is this? This is a semicircle, radius 1, centered at the origin, top half, but then moved up 1. So that means it looks like this. Semicircle just moved up 1. And so now your job is to find the area of this sort of composite shape, which is just a semicircle on top of a rectangle. And since the area of a circle of radius 1 is pi, this is going to be 2 plus pi over 2. Good. Next one is the integral from a to 2a of x. And okay, well, what do? We just draw the y equals x function, and I think it specifically says a is positive. So here's a, and then here's like 2a, so that's like 2a high and a high. So ultimately this is just once again a trapezoid, and was the area of that little purple trapezoid average of the bases times the height, but then this is just a, this is 2a, so the average of those bases is 3 halves a times the height of the trapezoid, which is just a, and so this is 3 halves a squared. This is just the area of that shape. Okay, so all of these problems involve just visual thinking, understanding that the integral is the area, and being able to construct little pictures of triangles and rectangles and trapezoids and circles and semicircles and quarter circles and such. Okay, last thing. There is the last 8 problems from this worksheet are an extended investigation of how basic graph transformations affect the area under the curve. So, time check. Everything takes longer than I wanted to. Here we go. You are just told that the integral from 0 to 1 of x cubed is 1/4. Okay? Great. I could do this with a Riemann sum, but I'll accept for the moment that this is just true. I've either done, actually I think this is just a problem from your quiz. So you are going to all do this. Perhaps you've done it already, demonstrated that this is true, using limits. But for the moment, we'll just take it as given. And now we're going to do 10 things. Dare I try to squeeze them all into this board? I feel like I should. Okay. So once I sure. Okay, so I think I've already made a terrible error. Oh my god. Let me just do my thing and not worry about spacing and just kind of go. Okay, so good. I'll even make a picture of the sort of fact that I know. That the integral from 0 to 1 of x cubed is 1/4. Okay, well telling me that, what you're really telling me is that there's this shape out there, man. It's the shape of a cubic, and that this shape is 1/4 of the enclosing square. So here's a 1 by 1 square, and this cubic function is taking up 1/4 of it, which actually looks about reasonable. That this is 1/4. Okay, so if that's true, then we are presented with a whole bunch of other little things and asked to calculate them. Well, 11 says, what's the integral from -1 to 1 of x cubed? Well, okay, if you just know the x cubed function, then you just know that this function looks like this and is odd. And so finding the integral from -1 to 1 of any odd function is going to just be 0. So actually I didn't even need to use this fact to conclude that this integral is 0. It's just true, I just needed to know that x cubed was an odd function. Okay, good. One down more. What's 12? I guess I'll do these here. What's 12? 12 says, what's the integral from 2 to 3 of x minus 2 cubed? Okay, well now we can draw a picture of this and we can see what is the x minus 2 cubed function. It just moves the x cubed function over 2. So interpreting this, okay, so I know now that it's like this and other things. It looks kind of like that. But alright, this is sort of a crappy picture because I made it too small. I'm only interested in the function on the interval 2, 3. On the interval 2, 3. So this is 2, and this is 3. In other words, I'm realizing that asking for the integral from 2 to 3 of a function which is to move over 2, what you're actually just integrating is the exact same shape as the original function. I know this shape is 1/4, so this integral must be 1/4 also. Okay, good. 13 says, what's the integral from 0 to 1 of x cubed plus 3? Okay, and now you can either split this up into 2, probably the simplest way, or you can just make a picture of x cubed plus 3. What does it look like? It's just the x cubed function, but it moved up 3. So it's going to start at 3 instead of at 0, and by the time we get to 1, we're going to be at 4, but the shape is the same. And so what we are now being asked to find the area of is this composite shape, which is like our little cubic shape, sitting on top of a rectangle of area 3. And so the answer to this problem is just 3 plus 1/4, or 13/4. Okay, continuing, 14 is the integral from -1 to 1 of the absolute value of x cubed. Okay, well, we just make a picture. What does the absolute value of x cubed look like? Well, if x is positive, it's the same, but if x is negative, it becomes positive first. And therefore, the negative side of this graph is now going to look like the positive side. And so we have our shape, but then we have like a repeat of our shape on the left side. And so, essentially, this absolute value sort of transformation forces this function to be even, and if each of those shapes has area 1/4, then this whole thing is 1/2. Okay, 15 says, what's the integral from 0 to 1 of 1 minus x cubed? Oh, okay, well, that seems hard, but no, it's not. What does 1 minus x cubed look like? It's like the x cubed function flipped upside down and then moved up 1. So, when I plug in 0, I get 1. When I plug in 1, I get 0. But also, it's going to be like that. Okay, and so the area I'm looking for is this area. But if you fundamentally believe that that shape is 1/4, then that shape just lives, sort of via complementary thinking, right here. That blue complement is 1/4. The sort of the complement of the unit square, and therefore my shape must be 3/4, and that's the answer to this problem. So still knowing just this one integral, I can figure these out. Okay, 5 more. Taking forever. 16 says, what's the integral from -1 to 2 of the absolute value of x minus 1 quantity cubed? Okay, this is actually pretty challenging because of the sort of pre-calc A skills required to execute this. Basically, this is asking me to produce a graph of y equals absolute value of x minus 1 cubed, which is not a simple, easy, everyday type thing. And if this is my function, how am I supposed to construct a graph of this function? Well, to me, the way I would teach this if I was a pre-calc A teacher is to first consider, let's call it like, f1 or something, just x cubed. And, okay, we know what that looks like. It looks like this. Then consider, let's call it f2, a transformation of this. The transformation being x minus 1 cubed. And, well, what does that do? It moves everything 1 to the right. And so what we get is this function that looks like this. So, and then, okay. So that's x minus 1 cubed moved 1 to the right. But then, there is this absolute value sort of transformation, which says basically, which expects you to sort of appreciate what a new function will look like in which the input has been replaced with the absolute value of the input. I think this is one of the hardest things you do in like October of pre-calc A. And the way of thinking about this is to just consider the relationship between this f3 function and the f2 function. Well, if x is positive, it's just the same. So when I go to graph this, I realize that, all right, for positive x's, this is going to be just like the previous problem. Cha-cha. So